In this presentation, I will go over and clarify some of the points from your A22 organic chemistry, specifically the amino acids section. Now, again, you'll see underneath it a lot of the CA definitions, and you'll see there's quite a few of those in this particular section. Most of them hopefully will be familiar with anyone who is studying A-level biology, but again, there are specific things that CA require from their A-level chemistry. Look over those. So an amino acid is basically where you've got, as it says, an acid group. So we will see that's formed by a COOH, and then there's an amino group attached to it. So we think of it in terms of chemistry as being C, and then some other carbon chain, and then somewhere further along the chain you've got the NH2 group, and you'll see that we will name them specifically. Now, chemistry quite often goes with systematic names, which can be a little bit cumbersome, but they allow you to draw the structure. Biology quite often is trying to talk very quickly about two amino acids joined together, so they use common names for them. And you'll be familiar from your biology with names like glycine, alanine, and so on as being amino acids. Now, if we want to name those systematically, we can do our normal chemistry. So for example, glycine, here's the structure of glycine here, and glycine has got 1,2 carbons, so it's based on ethanoic acid, but on the 1,2 second carbon, you've got that that NH2 group, so then it would be 2-amino ethanoic acid. Now, that becomes a bit of a mouthful if you're trying to say 3 of these joined together, and so that's why biology tend to use the common names like glycine, alanine, and so on. Look at alanine. Again, the structure of it is shown here. So this has got 1, 2, 3 carbons. So this is based on propanoic acid, 1, 2, 3. But on the second carbon, that second one there, you've got amino. So it would be 2-amino propanoic acid. So there's the amino acids there, and you could try practicing those by giving the systematic names for them. And if you write those underneath, and then we will check them off in a moment. So the systematic names for these would then be this one, valine, which has got 1, 2, 3, 4 carbons in the chain. So that's going to be based on butanoic acid. On the second carbon is an amino, but on the third carbon is a methyl. So 2-amino, 3-methyl butanoic acid. Leucine, 1, 2, 3, 4, 5 carbons. Again, a methyl group on the 1, 2, 3, 4th carbon, and amino group on the second one. So 2-amino, 4-methyl pentanoic acid. And serine, 1, 2, 3 carbons, so it's based on propanoic acid. On the second one is an amino group, and on the third one a hydroxy group. So this would then be 2-amino, 3-hydroxy propanoic acid. So you can give them systematic chemistry names as well. And as we say, in biology, they tend to stick with using those sort of more common names like valine, leucine, serine, alanine, glycine, things like that. In total and biological system, 22 amino acids are coded for them. 20 occur naturally in humans. And amino acids you can think of as being chemicals, as we've had before. So they've basically got 2 groups. They've got an acid group, and they've got a basic group. So the basic group's the NH2 group, the acid group's the COOH. Now what it means is that with acids, that NH2 group can add on an H+, become NH3+. With alkalis, they can lose their H+, the COH can lose and become CO-. So a general scheme for them is that whenever you've got low pH acidic solutions, you have lots of H pluses present. So that amine group will absorb those and become NH3+. So in low pHs, amino acids tend to sit like this. At high pHs, where you have lots of OH-, then the H pluses would have reacted with it and formed water, so they're being missing. So the NH2 would be the group there. And then you would also have the H plus coming off the acid, so CO-. So negative ions, say it again, negative ions at high pH and positive ions at low pH. And what about in between? Now the actual position, it says here about neutral pH. Well, it's closer to neutral. It depends very much on the chemical structure of the amino acid, but somewhere around neutral, you actually get a situation where both of those could happen. The COH could have lost its H plus and the NH2 have gained it. And when this was first described, this was described by German scientists, or was named by German scientists, who called these Zwitter ions, Zwi being 2, so ions with 2 charges. And basically what's happened is, whenever you've got the Zwitter ion, the H plus has come off the acid group, gone on to the amine group, and become NH3 plus and COO minus. Now, overall, these are neutral. So you can do things like electrophoresis and so on in biochemistry, and these won't move because the positive and negatives cancel out. But under neutral conditions, you've got these Zwitter ions being present. Now, what it means is that amino acids have really high melting points. And the reason for that is that if you imagine that you've got amino acids, then they've got 2 ions. And what it means is there's going to be ionic interaction between them. So there's the general formula for one amino acid. So the COH has become CO minus, then it has become NH2 plus, NH3 plus. The hydrogen, which is the normal bit with the amino acids on there. And then you've got the alkyl group, or whatever the variable group is here. If you put another amino acid beside it, the plus and minus are going to be attracted. And what that's going to lead to is a very strong ionic bond between the molecules. Now, because the ionic bond is so strong, they have unexpectedly high melting points. If you thought of those as just being molecules with van der Waals and possibly hydrogen bonds between them, then you might expect that they would melt at round about, for example, alanine. It would be expected to melt about 200 degrees centigrade. In fact, the melting point is 315. It's over 100 degrees higher than that. And the reason for the unexpected high melting point is because of the strong ionic bond between the molecules. Amino acids are very soluble in water, so again, a synoptic type question could be to explain their solubility, and you can see fairly obviously it's to do with the ionic charge. And you remember the general rule for dissolving is like dissolves like, so ionic substances dissolve in polar solvents like water. When you're asked to explain this, explain the interactions. So 2, the plus charge on the NH3 plus is going to be attracted to the delta minus on the oxygen of a water molecule. The minus charge in the CO minus group is attracted to the delta plus of the hydrogen on the water molecule, and that means that the water will be attracted and mixed readily with water molecules, and hence it's going to be very soluble in water. So think back to how we answered questions of this type back in AS1 when we were explaining solubility, and again that could be a synoptic type question. The reactions of amino acids. Now, when we look at the reactions of amino acids, we have to think of them as really being 2 molecules. They've got a COOH group, this group here, so it acts as an acid. So, for example, sodium carbonate. And when you mix sodium carbonate with amino acid, now I've put there that fizzes. Generally, it's not quite strong enough to fizz and give it off, but sometimes some textbooks will talk about it giving off the carbon dioxide and testing for that with lime water, so I've included that. But basically it acts as if it's a COH group, as an acid group. And what most common questions ask is they give you the acid group and then ask what it turns into, and if you've got a sodium carbonate or sodium hydroxide and so on, you'll get the sodium salt. So with alanine, you'll see again the equation for it. So alanine's the structure there, so we just simply put the bit of the structure onto it. Sodium carbonate, that would give you the sodium salt of the acid. So we've drawn the whole structure there and then just replaced the H with an Na+. With glycine, again, we've got the structure there. Again, sodium carbonate reacts, and you'll get the sodium salt of it. What I've been putting up each time as well is if you were to balance an equation, if we've got sodium carbonate, 2 of the sodiums in that mean that you have to balance it up by putting 2 in front of your acid there. The most common question that comes up in this is where they draw the structure and then ask you to draw the new structure whenever it's reacted with, say, something like sodium carbonate. With the NH2 group, the other bit of the amine, nitrous acid, you think of it as being an amine group, NH2. And if you remember with nitrous acid, what tended to happen with it is the NH2 got converted into an OH group with the evolution of nitrogen gas. So you got that fizzing. That was the test for the aliphatic amines, and the other product being water. So again, put in specifically, so this time if we do it for alanine, there's the alanine molecule, it's got that NH2 group, and you see that simply changes and becomes OH. With glycine, same thing happens, where you've got the NH2, and that becomes OH. So for both of these, watch out in exam questions, and you'll see that they'll quite often give you the structure of it. They'll say to you, what would be the new structure if it reacts with nitrous acid, or they could describe how you make nitrous acid. Remember sodium nitrite with hydrochloric acid to make that. Or they could ask you with sodium carbonate or sodium hydroxide, in which case it'd be given as that. So try and look at these as being the reactions of the functional groups. The other reaction of it is with copper sulphate and glycine, and there's a very specific reaction with it. Now, I've put a link into the PowerPoint there to one of the Frankly Chemistry videos, and you could take a wee look at that, and it'll maybe explain a wee bit more about that sodium carbonate reaction in detail. And what it shows very nicely, I think, is the reaction with the copper. So I'll play that little bit of the video. You'll see I have it paused here, and I should be able to play this, and this will show the reaction. So I'll show you this just for a moment or two.
Right here, let's take a look at copper 2 sulfate solution. It's a light blue colored solution. And in the other test tube I have a colorless clear solution of glycine. Let's see what happens. You see that light blue solution turn dark blue in color. To fully understand what's going on here, one would need to have studied metal complexes, transition metal complexes in advance. In copper 2 sulfate solution, the copper ions do not go around as separate copper ions. Go around surrounded by bond 2, 6 water molecules known as ligands, and we have what's referred to as the hexa-aqua copper 2 ion shown in square brackets there with 2 plus outstanding. And what happens here is actually known as ligand exchange. We have those 6 water ligands replaced by 2 amino acid ligands. Now the amino acid, you'll see, behaves as a so-called bidentate ligand. Changes from being what's known as 6 coordinate on the left to 4 coordinate here on the right. Watch how on the right here we have a glycine molecule coming in, and note that it forms 2 coordinate bonds with the copper 2 ion, one through the lone pair on the nitrogen of the amino group, and the other through the lone pair on the oxygen of the OH of the carboxyl group. And then let me bring in a second glycine molecule. And again, it forms 2 coordinate bonds with the copper. We've changed from what's referred to as a 6 coordinate metal complex on the left to a 4 coordinate metal complex on the right. Just as water ligands are neutral, in this case the amino acid ligands are neutral as well, so the charge on this metal complex is still 2 plus, you'll note. And we have displaced or exchanged the 6 water ligands. That's been my look.
Okay, so you will see then that's the reaction with the copper sulfate. So let's get rid of that. So there's our shortened equation of it. So the pale blue copper solution you saw in the video showing as hexa aqua, so copper ions surrounded by 6 water.